This is the Team 14 presentation for the mini bike drivetrain design. The members of Team 14 consist of Dylan Hewitt, myself, who was the lead CAD designer and a co-media producer. We also have Declan Moll, who is the lead designer of the bike and our machinist for actual production of the bike. We also have Aaron Nagy, who is our bearing mechanism designer. We have Austin Kane as our braking mechanism designer. We also have Trevor Winchester as our flexible mechanism designer, specifically chains. And we have Julian Sleeman as our lead media producer and co-CAD designer.
The mini bike was developed and built by one of our own team members, Declan Moll. The three mechanical elements are presented below. We have ball bearings, flexible chains, band brake, more specifically using a V-belt, along with their respective illustrations.
The original idea for the mini bike began 10 months ago, as Declan Moll began the process of fabricating a mini bike chassis from common materials. The main design requirements were that the mini bike was compact in size, cheap to maintain and manufacture, and be rugged yet simple to operate. Several mechanical elements, such as the wheel and tire size, engine, and type of clutch, were pre-selected based on prior experience and availability. Preliminary research conducted found that due to predetermined frame and tire dimensions, it would necessitate the use of an intermediate shaft to transfer the power between the engine and the rear axle. The following report will dive into the analysis, calculations, and results.
We opted to design a drivetrain for the mini bike for a few reasons, such as it is important there is no slippage with the torque delivery so that all of the torque and power can be transferred to the rear axle. Using a chain also allows for us to use the mechanical advantage that comes with the gear ratios to increase the top speed. The current top speed of the mini bike is around 40 kilometers an hour. Chains are also cheaper than belts for the required specifications, and the chains are easier to take care of and maintain. This analysis was centered around minimizing the cost of the chain. The chain only needs to last until another component of the mini bike wears out. We determined the desired life of the chain to be around 800 operating hours at a sprocket speed of 2000 RPM. A chain that is stronger will last longer but will not be of much use for us, and it will cost more. That is why we selected the ANSI 35 chain as the optimal chain to use and calculated its approximate lifetime.
Our mini bike contains an unconventional and unique V-belt sheave brake. The objective of our brake was to create high braking capacity for a given application force. A V-belt brake allows for this due to the wedging nature of the V-belt and sheave, as well as the intermediate shaft containing a torque multiplication to the rear wheels from different diameter sprockets. The design is simple, inexpensive, and adjustable. Though it can produce rubber debris and is noisy in operation, the system is also reliant on the rear chain, which if damaged would make the brakes inoperable. Lastly, the V-belt section would require frequent changing. It can be seen that a few values have been tabulated to see the effectiveness of the brake. For emergency use, wheel lockup can be achieved from an application force of 0.71 pounds, which produces 39.4 pound-foot of braking capacity at the rear wheels. Although not recommended, the brake can easily combat engine torque with a mere half pound of force. If accelerating while braking, 1.22 pounds is necessary for emergency rear wheel lockup, producing 95.1 pound-foot of braking capacity. In order to avoid a breakage of the V-belt, one must not exceed an application force of 4.77 pounds, which can produce a braking capacity of 372.6 pound-foot. Please note that an equivalent braking capacity can be achieved by a similar force at a radial arm of 78 feet on the rear axle. At this point in time, we do not know the reliability of such a braking system, and thus further testing should be done. An innovative design nonetheless.
Although bearings do not have a direct effect on powertrain performance, they are a key mechanical element that allows the system to operate smoothly and reliably. After the bearing reaction loads are determined from the brake and power delivery system, their selection process begins. First and foremost, the maximum average bearing loading condition was determined to be under steady velocity. Additionally, the mini bike is predicted to operate on uneven terrains where it would encounter light impact, which is considered in the analysis. The team deemed that using homogeneous bearings throughout the mini bike is required. Consequently, bearing selection was limited to 17mm bore by the pre-selected shaft size. The result for deep groove 17mm bore is shown in the table along with a life comparison between both manufacturers. Although Timken bearings come at a premium price, they are also 77 times longer. They also last 77 times longer than other competitors who have their maximum life of 98 hours. For these reasons, the team decided that Timken's bearing life outweighs its cost. For machine reliability of 99%, 4 17mm deep groove Timken bearings are selected. This bearing will support a maximum cornering acceleration of 0.88 meters per second squared, which will induce a maximum allowable axial force on the bearings. Recommendations for bearing life and replacement will be included in the instruction manual.
In summary, we've selected 4 Timken Deep Groove 17mm bore ball bearings for use on the 2 shafts, 2 for the rear axle and 2 for the intermediate shaft. We've selected an A-type V-belt for use in our V-belt brake, and we've selected an ANSI 35 chain, one with 51 links and a second with 58 links for the main and secondary drives, respectively.
When we look at the mini bike driveline design, our group has effectively implemented cost minimization strategies through the selection of 4 identical wheel bearings, the standardized use of ANSI 35 chain for the primary and secondary sprocket sets, and a common supplier for bearings, pulleys, chains, sprockets, and fasteners, being Princess Auto.
As engineers, we are all part of a professional society. The professional societies offer different benefits. So for the engineering society, it has its own benefits, and these benefits can be listed here and are also as followed. The benefits that come with include an online forum to discuss all sorts of engineering-related topics, which was used during this project to look at further research and development on the bike, help throughout your engineering career to find new skills and jobs, such as through their career events. It also offers member perks that include discounts and rebates on services and products, and insurance tailored for engineers. The engineering societies advocate for their members by dealing with issues felt by members and may oversee other bodies, including governments. What is the Ontario Society of Professional Engineers? Well, the Ontario Society of Professional Engineers has a vision, mission, and a values. Their vision is to have a diverse and inclusive profession where bold, courageous, and respected leaders who are engineers come together to collaborate with government, industry, and academia to solve new problems with innovative solutions. The mission is to advocate on issues of importance to society and the engineering profession, and to create opportunities for all engineers to be able to collaborate with one another. The values that they have is that engineers are obligated to lead and to solve problems through collaboration, to become more equitable, diverse, and inclusive in order to thrive, and are guided by factual evidence only. That's it for our presentation. Thank you for listening. Here are the references used below.